Hello, everybody. Good afternoon. Thank you for all coming along. Firstly, I'd like to acknowledge the Wurundjeri people of the Kulin Nation, on whose lands we're meeting, the beautiful Yarra River. I'd like to thank them for their love and care of this land since time immemorial. I'd also like to just acknowledge the folk at ABC who are going through a very tough time at the moment, and my heart and thoughts go out to you, especially for any of you here today. I got out of COVID lockdown on Sunday, and yesterday I did a presentation and only just got through it, I think. So I thought, I'm doing okay, I'll come along today and it'll be fine. And then someone at lunchtime said, Ben, you have the worst brain fog I've ever seen. So we'll just have to see how it goes, hey? I'm not really intending necessarily to go through the paper, as it stands. You can read it, but I thought I'd take the opportunity talking today just to maybe take a step back and sort of like Kathy did, take a little bit of a wider perspective on machine learning and have a bit more of a chat about what it is and just break it down a little bit. And she said, I'm not going to do any scary maths. I thought maybe I'll do a tiny little bit of scary maths, but no, it won't be scary. It'll be maths, but not scary. Okay. So the story is that I'm a tragic lifelong learner. So when COVID lockdowns came along, after we had the kids sorted out doing their schoolwork, not doing their schoolwork, I got a high school maths textbook and went through it. And then I thought, I'm going to enroll in a Masters of IT at Melbourne Uni, specialising in artificial intelligence. So I did that for a little while until I realised that's an absolutely crazy thing to do during lockdown. And I stopped doing that. But I got a little bit done. And so this project was sort of me tinkering a little bit. It was a little bit of an experiment. And I just wanted to get those learnings out and have some kind of product of that time, which I found so fascinating. I'd like to continue that when the opportunity comes along. So this project is the outcome of that, seeing what I could do in that space and play around. So just a real quick background. I'm from Education Services Australia. We are a government-owned not-for-profit. We're established by the state and federal education ministers, to whom we still report. And we essentially deliver solutions, technology solutions for the K-12 educations, not just K-12, but predominantly K-12. One business unit within ESA for which I'm responsible is SCIS, or the Schools Catalogue Information Service. We're coming up to our 40th anniversary. So essentially what we do, or have done since the early 80s, is create records for school library catalogues. So what that means since the 90s has been delivering MARC records. So we do the original cataloguing. Schools subscribe to us and download the records for their local systems. Brain, go. So that's what we've been doing. That's our business model. We have about 80 to 90% of Australian schools subscribe to us, about 50% of New Zealand schools, and schools in 26 other countries. So we're really, I guess, an international cataloguing service. Let's do a quick segue now. Machine learning. We'll come back to SCIS and what we do and this project in a little while, but let's jump to machine learning, and it's bandied around, and I just am so grateful to have had Kathy presenting earlier today, because it was just such a beautiful introduction for me to come in. I thought I'd put this image up first, because this is often the sort of thing that you see and it looks very technical and scary, and it is a little bit technical and scary. This is an image that's often used to illustrate an approach to machine learning called neural nets. So some input goes in one side, the computer does all this stuff that's sort of analogous to a human brain, and then stuff comes out the other side. And it's a big black box what goes on in there, and it's complicated. But machine learning doesn't need to be this complicated, and it can actually be quite straightforward and a bit intuitive. And so I thought I'd step you through some of what I did to illustrate that it's actually doesn't need to be complicated like this. So what is machine learning? There's lots of definitions, but here's one. Methods that leverage data to improve performance on some set of tasks. So that doesn't sound too scary. It's broadly artificial intelligence. I don't actually think there's anything too intelligent about it. It's just the same thing computers have always done. It's data and they crunch it and something comes out the other end. But it's a set of computational methods and statistical modeling that uses training data. Not all machine learning approaches use training data, but predominantly. Kathy put a model up for one that's called reinforcement learning that doesn't rely on data to go in at the start, but so there's exceptions to the rule. But by and large, training data is used to optimize a predictive model. And of course, these days, there's lots of internet data, so there's lots of data to be had. And so this idea of big data comes into it. And there's different ways or different methods of doing machine learning, different algorithms or approaches. And essentially the one that's used depends on what your problem is or what the task is that you want to undertake. And there's actually quite a small, limited set of tasks that machine learning undertakes. And I'll step you through some of the big ones now, just as a quick overview. So a predominant machine learning task, a common one is called clustering or similarity. And all we're doing here is we're saying, we've got this new thing. How does this new instance of a thing relate to existing instances based on what we know about those existing ones? So a good example is a recommendation engine. We know you watch this show. What else do we think you might like based on what we know about the things you've watched before? A second task is classification, and that's relevant to what I'll be talking about today with my little project. A common implementation of that is for image recognition, for example. So what category does this new thing belong to based on what we know about existing things and the categories they belong to? So we've got lots and lots of images. These ones are images of cats. These ones are pizzas. We know all about them. So you've given me a new image. Which one is it likely? Which category does it fall into? And a third machine learning task is numerical prediction, or what's called regression, and this is a numerical value. So what value can we expect for this new instance based on what we know from existing instances? And an example might be travel time. Like, we've got all this data about how long it takes to get from A to B for these other journeys at different times of day and traffic conditions. So given this new one that the user's giving us, what time would we predict for this one? So machine learning has been used for a whole bunch of bibliographic description problems. I'm not going to go through all of these. I talk about them briefly in my paper, but you can look them up. Anyone who was at Adrian Kelly's presentation earlier, he talked about a specific application that sort of falls within this as well in terms of describing images. He used a commercially available third-party product to do the machine learning. I do it from scratch. That's all right. No, that was a great presentation. He talked about some of the dangers and pitfalls of that, and I really enjoyed it. And so, yes, increasingly being used in this sphere. So essentially, what did Ben Chadwick get into his head to do while he was in crazy COVID lockdown? So I thought, well, what if we can take a book with the traditional cataloguing data that we know about it and get a computer to tell us what Australian curriculum learning area is this book probably relevant to? So is this book relevant to learning mathematics, for example? So this is a classification problem. And essentially what we could do, just to get it right down to the basics, is we could get 10 books and we could get an Excel spreadsheet and we could say, let's look at these books. Which ones are related to maths and which ones aren't? We've got a pile of 4 that we're saying yes and a pile of 6 that are saying no. And that's essentially a very, very basic machine learning model done in Excel. So if we get a new book, hang on, I was going to talk about some terminology first. So let's talk about some basic terminology. So if we're in the machine learning world, we'd say the thing we're trying to predict here, mathematics, is called the label. The 10 books that I have are my training data, and there are 10 instances. So that's the jargon there. We have instances, not books. And we have 2 classes. So within that label, there are 2 classification options, yes or no. So there's some jargon. The label, the instances and the classes. And so for this is a very dumb algorithm. Or what we can do from this is we can look at, well, 0.4 of the books are related to maths and 0.6 aren't. So if we get a new book in, what would our algorithm tell us? Well, it would tell us in every case the book probably isn't about mathematics, right? So it's data, it's an algorithm, but it's a really, really dumb algorithm. But it is actually one that's used. It's called the 0R or majority baseline algorithm. And it's used as a baseline to compare other better algorithms to say how much better is this algorithm based compared to the 0R baseline. So, all right, so far we can do machine learning in a really dumb way just with an Excel spreadsheet. But obviously it's get more complicated. So now we're going to add some data to help us predict whether this book is related to mathematics or not. And we're going to bring in what's called features. So here we have 3 features. And in our example, we're going to say our 3 features are, we're going to look at the very broad Dewey classification, so just at the hundreds level. We're going to look at the subject headings. Does the book contain a subject heading with the word algebra in it? And does the book contain a subject heading with the word formula in it? And we're going to try to use this information to predict whether the book is relevant to maths or not. And now we're going to do some very basic mathematics. We're going to look at the proportion of those books related to maths. Let's look at the proportion that do have the word formula in them. 3 of them do, 1 of them don't, so that's 0.75. Don't worry, you don't need to follow this. It's just illustrative. Then we're going to do the same things for not mathematics. Only 1 of them does, 5 of them don't, so that's 0.133. And then we do that same calculation for all of our features. So we've now got a table of probabilities. So now when we get a new book that comes along, this new book doesn't have the word formula in it, it doesn't have algebra, and it's got the Dewey classification in the zeros. How likely is it that this new book will be relevant to mathematics? And all we do is plug some of those proportions into a formula called Bayes' theorem, and it tells us the probability that the book is related to maths and the probability that the book isn't related to maths based on that feature set in our training data. And in this case, it would say, no, the book probably isn't related to mathematics. So you can see what Kathy was talking about here, that it's about probabilities, it's all probabilistic, and it's entirely dependent on the feature data that we feed into the system. And this is, in fact, a tried and true, often used machine learning algorithm called naive Bayes classification. So if you look into the literature, you'll see it all the time. And the maths behind it is quite straightforward. And it illustrates that for this kind of classification problem, this is called a supervised learning problem. It means that the data we're using, we need some test data that's labelled. So training data, labelled training data. The data that we feed in to train the algorithm needs to have the answer in it. So we have a set that tells us, yes, it is related to maths, or no, it isn't. All right, that's the basics. From there on, it's just scaling up. So we might add more labels. We might say, okay, now we're interested in not only maths, but science and English as well. So now we have what's called a multi-label problem. And then we add more features, and we add more instances, and we add more labels, and the data set gets bigger and bigger, and now we're probably going to struggle to do it in Excel, so we're probably going to use Python or R or some other specialized software to run this sort of algorithm. But the basic idea at the center of it is still exactly the same. So getting back to what I did, the Australian curriculum has 9 learning areas: English, mathematics, science, humanities, the arts, technologies, health and phys ed, languages, and work studies. We've known for a while that our subscribers would like some kind of information when they come into our catalogue about to narrow down their search or to browse on the basis of learning area that resources are relevant to. So we do actually have that data in our catalogue at the moment. It's not created by our cataloguers. It's actually created by a rules-based algorithm. So that's slightly different from machine learning. It's just a series of if-then statements. So it's saying, if this resource has this Dewey classification, we'll say it's relevant to English. If it's got this subject heading, we'll say it's probably relevant to science. So it's a pretty dumb mechanistic algorithm. But it's doing the job. But it got me thinking, is this the kind of problem we could bring machine learning in to either replace this process or to supplement it in some way and make it better? The problem is that we need that labeled data. So we need that training data that I told you about before. And I don't want to trust that rules-based data to build up a machine learning model. I want some good, sound, best practice data to use as the training data. And SCIS doesn't have that. What does have it, though, is a different system we use at ESA. This is called Scootle. This is a repository of digital learning resources for Australian teachers. It's got about 20,000 online digital learning resources in it, and each one of those is tagged with learning area data, and it's applied by subject matter experts. So it's gold standard practice in terms of the metadata being created there. Importantly, every Scootle resource is also tagged with topical headings from this Schools Online thesaurus. So that's a vocabulary that I'm responsible for, and it's a thesaurus of topics in the education space. So every Scootle resource has one or more Scott headings to describe the topic of that resource. I know how bad it is at the back of the room and that you can't see this stuff, so I'll try to read it off. So there's a screenshot from Scootle, and it's saying this particular resource is about text structure, reading comprehension, and text types. So those are all topical headings from the Scott vocabulary. Now, the reason I bring that up is because SCIS records are also tagged with headings from the Scott vocabulary. So we've got this common data across both data sets. So that gets me thinking now. We've got the labeled data in Scootle to tell us about learning areas, and we've got a feature set that we can use, namely the Scott topical headings, across both data sets. So what if we could build a machine learning algorithm over here in Scootle data and then apply it over here to the SCIS data? And that's what Kathy was talking about when she said classifiers or machine learning or the agents are built in one environment and trained in one environment, and they're set loose or set into the wild in a different environment, which can have problems, which we'll talk about. But that's the general idea. So just to ram this home, what was the project? We wanted to develop and evaluate a machine learning algorithm to classify our SCIS records according to the Australian curriculum learning areas that they might be relevant to. We wanted to train that classifier on the Scootle data in the Scootle repository. We were going to use the Scott topical headings as our features to train it on. And we used two algorithms. This is common in the machine learning literature. They might use a bunch of different algorithms and compare them to see which one worked best. It's not so important for our purposes today, but in my paper I used naive Bayes, which I talked about before, and a different algorithm called logistic regression. Why do this? Well, it's a proof of concept. I guess it's asking the basic question, how could SCIS use machine learning to support and supplement the work that our cataloguers do? It's a little project that's sort of achievable. It's low stakes. Nothing bad will happen if this doesn't work. But it's still relevant to our work and our core sort of objectives. And it's supporting some of SCIS's long-term strategic objectives in terms of looking at how we can utilise technology to improve our processes and add value to our products. So again, just driving it home, I wanted to classify resources in our SCIS database according to the relevant learning areas. So again, this is a multi-label problem. They could be related to mathematics and or science and or English and or all the way through. The problem is we couldn't use the SCIS data as training data, so we went over to a different data set where that labeling did exist. We'll use that as our training set, and then we'll apply the classifier back to the SCIS data set. The reason we could do that was because both data sets have the Scott topical headings. But there are differences between the data sets too, and that's an important consideration that comes into play. Different description standards and metadata standards, different subject description practices. The Scootle data tend to have more Scott headings. They're applied a bit more loosely than in SCIS, where they're applied quite tightly. And there's different resources in the two data sets. Scootle is all online learning resources. SCIS has that stuff too, but it's also a lot of hard copy books, etc., and a broader diversity of resources in the SCIS database. Is this 9 minutes to go, or that I've been talking for 9 minutes?
Probably 9 minutes to go.
Okay, that's pretty good. All right, thank you. All right, results. Oh, that's why it went from 10 down to 9.
Probably.
COVID brain, time. All right, the results. So I'll talk about this fairly briefly because it's described a lot better in the paper. But essentially there's two metrics, key metrics when you're looking at an algorithm and how it performs. One is precision and one is recall. So precision is all about how accurate was the algorithm. Did it misclassify things? So of all the things, for example, that it said were about English, how many of those weren't really about English? How many false positives were there? Recall is the sort of flip side of that. It's about gathering the net of all the resources that were English. How many of it did it get? Were there ones that it missed out on? So it's about completeness of the retrieval process. And so it's the balance of those two metrics that tell you how successful the algorithm was. So in the paper, I have these sort of spider graphs and stuff, and you can look into that. But the take home is that when we built the classifier on the Scootle data, the precision was actually pretty good. So it didn't often misclassify. And that was especially true in mathematics, humanities, science, and English. So why those ones? Well, they had a lot of data. So the more data, the better. Unfortunately, technologies and HPE didn't have a lot of resources that came out of Scootle, so the training data set was smaller and the precision wasn't as good. But the precision was better than the recall. So the recall, again, the recall was pretty good for maths, languages, humanities and science, but not so great for the others. In fact, not a lot better than our 0R baseline that I told you about earlier. So again, it's about the size of the data set, but the general take home was that it's good for saying that something, if it says that something is to do with the learning area, it probably is. But it might miss out. There might be stuff missed out on. This is starting to sound like rat tests now, isn't it? Okay, so part B was the same thing. We used the same algorithm, but now we let it loose in the wild. We set it loose in the SCIS database instead. So can that classifier now be used on the SCIS records? So what I did was found 14 resources in SCIS that were clearly and only about one of those learning areas and one only. So I manually eyeballed each of these and said, yes, this is about English. It's not about maths or science. This is about humanities. It's not about the arts. So we had a data set of only 104 records in SCIS to test the classifier on. And the results, the same picture emerged, but just worse. So the classifier was better for precision, and for languages, maths, and HPE and arts, actually, it had very good precision. So again, it wasn't misclassifying anything. It wasn't saying this is about HPE when it wasn't actually about HPE. But the recall wasn't great, so it had a bias towards rejecting things. It felt a bit tentative, and it said, "Oh, okay, I'll say it's not about anything then." So that was the outcome. So it was, sort of successful, but we need to think about what the ramifications are here. Obviously, the chief takeaway is we've got to have a nice big data set. So the next thing that I would do, if I was to follow this up, is to find more data, more training data. That's not going to come from Scootle. Potentially, we could do this in SCIS. We could start getting some experts in, for example, and classifying our SCIS records according to learning area and make that our training data set. That would be a big undertaking, but it's all about priorities, isn't it, and funding and seeing what you want to do. So as it stands, this application I wouldn't say is ready to go into any sort of production use. Having said that, it kind of maybe could for maths, humanities and science and English. It was actually working fairly well for those 3 learning areas, but that's a sort of limited application if you can only use it for 3 and not the others. Where it was looking good is maybe as sort of like a screening tool. So given that the precision was good but the recall wasn't great, it would actually be okay as a second sort of filter around the rules-based approach. So it could sort of say, the rules-based approach has said that this book is about HPE, but I don't think it is. And then that would flag it for someone to sort of manually check, or maybe it could just rule it out. So maybe it's a screening approach. Why did performance deteriorate when we went from the Scootle dataset across to SCIS? Well, it's probably to do with some of those differences I brought up before. The classification practices are different, the resources are different, so different environments, and Kathy sort of referred to this in her keynote. What would I do now? Well, yeah, I'd love to maybe start getting this sort of data that we can use from the SCIS dataset and actually comparing and contrasting how machine learning performs compared to the rules-based approach. So is one better? Can we make one better than the other? And there are a couple of papers in the literature showing that when you've got enough data, machine learning does outperform rules-based approaches. We could also bring new features in. So rather than just using topical headings, you could text mine the titles of books, you could text mine the summaries and descriptions, you could bring the Dewey in. So all kinds of pieces of information that you could use as part of your features to train the classifier. And it broadly asks, you know, what other applications could we use machine learning for to improve workflows, add value to data, and reduce repetitive and low-level tasks? And I know this is quite a fraught area. I was listening to News Breakfast this morning. I heard Ida Buttrose say, the reason we can let these staff go is because we've digitised everything at ABC. Now that everything's digital, we don't need them anymore. So there's a lot of important questions we need to ask about this technology, but I think there are ways that we can see that it can supplement and enable staff to focus on what they're really good at and reduce and minimise low-level or repetitive tasks. But it's something we need to think about carefully. Thank you very much.
Thank you. I'll just use this one to give you a little bit of space. Yeah, they all work, don't they? I probably should have clarified to Ben that 9 minutes was for the whole session, unfortunately not for his presentation. We have run out of time for questions, unless there are any really burning ones, and we can squish them in before we run across the next session. But thank you so much. That was absolutely fantastic. Please allow me to present you with this pin on behalf of Vala. I'm trying not to get too close to you. No, not infectious. But it's more in terms of the feedback of the microphone. But thank you so much. That was fantastic. I do have a sneaky question that I'd like to just pop in before we head off. One of the takeaways from Kathy's sort of presentation is that there's no minimal technical skill level for us to start engaging with this process. So you mentioned as well that you did get to make the most of lockdown, and you did a partial master's, and you did go away and learn things. What was one thing about that surprised you that you already knew from that experience in terms of your background working in this space?
Yeah, well, Kathy mentioned that, you know, we're data experts, and a large chunk so if you go into a program like the one I started and do a subject along the lines of Introduction to Machine Learning, half of that subject will be about different data types and the work needed to refine data and tidy data. And it's just what we do. So you can get halfway through an Introduction to Machine Learning course before you get to any maths and go, this is basic data management librarianship. So I really related to what she said there and completely agree with that. Yeah.
The future is ours as information professionals, and it's never too late to return to the maths. It's all possible. Thank you so much, Ben Chadwick. Another round of applause for Ben.